The lesson topic for this video is probability and odds with calculated sample space. So this lesson is going to be a continuation of our work with probability and odds, but this time our sample space, or the number of outcomes in our sample space, will not be as readily available. We're going to have to calculate it. So let's go ahead and take a look at our first example. Here's the setup here. There are some students waiting in line for a bus. 3 are wearing Osseo orange, 4 are wearing Viking purple, and 1, though we do not understand why, is wearing Pecker green. Okay, so I'm actually going to jump down to the question number 3 here and look at this question. Okay, because this is actually the question we're trying to answer, and the first 2 questions are going to help us get there. So question 3 says, what is the probability that the students wearing orange are standing in the first 3 spaces? What's the probability that that's how they are lined up? Okay, if you think about it, if it's just this random group of people standing in a line, it's not super likely that the 3 wearing orange are going to be in the front. Okay, and what we need to kind of ignore in this problem is we're not going to take into consideration that the 3 people wearing Osseo orange might all be from Osseo and therefore they are standing together because they're friends. We're going to take that idea out of this. We're just looking for the mathematical probability. Okay, so thinking about probability, we know that probability is a fraction, and in the numerator we need to know how many ways can that happen. How many different ways are there that the 3 students wearing orange are standing in the first 3 spaces? And in the denominator we need, what is the total number of possibilities for that line? How many different ways can those students line up? Okay, that's what these 2 questions are going to answer for us. The first one says, in how many ways can the students line up? That is going to be our sample space, the total number of ways that they can line up. So, as we've learned, if you're lining up students, we're talking about a permutation. So we're going to go ahead and calculate that as an NPR situation. I'm actually going to show you another way to figure that out as well, or remind you that the fundamental counting principle is another way that we can use, another method we can use to calculate the sample space. So NPR, remember, is the number of items that we've got that we're arranging, and R is how many we are arranging out of the total number that we have. So since we have 8 students, let's look at this. 3 plus 4 plus 1, 8 students. So since we have 8 students and we're arranging all 8 of them, we need to calculate 8P8. When we calculate that, we get 40,320. Sorry about that. 40,320. There are a lot of different ways that 8 people can be standing in a line. Now, the fundamental counting principle could have been used here as well, and that is that idea that we can think about the line as being 8 blanks that need to be filled. So there's 4, 5, 6, 7, 8. Okay, how many people could stand in this spot right here? Well, there's 8 people that could be standing here, so that is 8. Okay, once that person's standing in first in line, how many different people could be here in the second spot? Well, that'd be 7. And then there'd be 6 left for the spot, 5, 4, 3, 2, and 1. And the fundamental counting principle says that we can multiply all of these up together and get the total number of ways that the students can be lined up. Again, the answer is 40,320. Okay, so now what we know is we know that the denominator of this fraction of our probability is going to be 40,320. Because if we're trying to find the probability that the students wearing orange are standing in the first 3 spaces, we need to know how many different ways the students can stand in all 8 spaces, so 40,320. Now our job is to find out what the numerator is. How many ways are there for the students who are wearing orange to be standing in the first 3 spaces? Again, I'm going to show you 2 different methods for calculating this. First, I'm going to use permutations again. So, if we need the first 3 students, if we need to find out how many ways that 3 students can be standing in the first 3 spots, and then we need to find out how many ways there are for the remaining students to stand in the other 5 spots, we're going to do a multiplication of two different permutations. We need to know how many ways 3 students can be arranged out of the 3 students who are wearing orange, and we need to know how many ways that 5 students wearing something other than orange are arranged if I'm arranging all 5 of them. And then, since it's 2 different let's say events that are going on, the first 3 people who lined up and then the next 5 people who lined up, and you heard me say and then the other students who are lining up, we're going to multiply our permutations. So the first thing we need to do is calculate 3p3. And 3p3 is 6. And then we have to multiply that by the total number of arrangements that the other 5 people could be in, which is 5p5, and that's 120. If I multiply 6 times 120, I get 720 different ways that the first 3 people could be in orange and the remaining people would be in the 4th, 5th, 6th, 7th, and 8th spots. Now, like I said, there's another way to do this, and some of you might like this method better, and this is again using the fundamental counting principle. We still have 8 spots, right? 1, 2, 3, 4, 5, 6, 7, 8. But this time, we want a specific set of 3 people to be standing here to find out how many ways this can happen. So the first 3 spots, we're saying we want to know how many ways it can be that they're wearing orange. So our first blank here, how many different students could stand here if we're trying to find out how many ways that the first 3 people can be wearing orange? Well, there are 3 people wearing orange. So there's 3 people that could stand here. Then how many people are remaining wearing orange? Well, 2. And how many people are remaining that are wearing orange? 1. So 3 times 2 times 1. And now we have to figure out the rest of the line. Okay? If these 3 people are already standing here, how many people are there remaining to stand here? Well, 5. So there are 5 people that could go in this spot right here. And then there are 4 people remaining after that to go here, and then 3 people, and then 2 people, and then 1 person is remaining. If we multiply 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1, we are going to get 720 ways. The same answer as we got when we did the permutation work here. Both of these ways work for both part 1 and part 2. So now what we know is we know there's 720 different ways that the first 3 spaces could be all people wearing orange and the rest of the spaces be people who are not wearing orange. So we have 720 that goes in the numerator of our fraction. So it says, what is the probability that the students wearing orange are standing in the first 3 places? Well, there's 720 ways that that can happen out of a total of 40,320 ways that those students can be standing in a line. If we want to simplify this fraction, we can, and it does simplify to 1 over 56. So the probability is 1 out of 56 chances that the students wearing orange would be standing in those first 3 spaces. By the way, if you're interested, that is about 1.8% if we divide it. So 1.8%. Not very likely that that line of 8 people would have all 3 people wearing orange be first, second, and third in line. Okay, one more example, and I know there's several parts, but only one more example for this lesson. First of all, you have a standard deck of playing cards, which is 52 cards. There's 13 hearts, 13 diamonds, 13 spades, and 13 clubs. Now, if you don't know much about a deck of cards, I will try to have something, available for you. I'm trying to help you see this. Isn't that awesome? There we go. All right, so there's a deck of cards, just in case you're not too familiar. We've got the ace, which is like a 1, all the way through 10, and then what we call the face cards, jack, queen, king. These are the diamonds. Then we've got the hearts, the spades. So this shape right here is a spade, okay? And then the clubs. All right? So if you're not too familiar, you might want to find a deck online, just kind of look at it like this, or refer back to this point in the video. All right, so I'll minimize this, bring it over there, bring the questions back. So, how many 3-card hands are possible? So a hand in cards just means what is in your hand. Think about it for a minute. If you're holding 3 cards in your hand, the order is not involved. Okay, the order is not important. If I have a king, a queen, and a jack, a queen, and a king, let's say, a jack, queen, and king, it doesn't matter if I have jack, queen, king, or king, queen, jack, or queen, jack, king, or queen, king, jack. It doesn't matter. It's all the same 3 cards. So if you think about that, we've got a combination situation. Now just to note, the fundamental counting principle can't be used when we're talking about a combination. That only works with a permutation situation when we're talking about order. So, how many different 3-card hands are possible? Well, I could have an ace and a 3 and a 7, or I could have a king and a jack and a 4, or I could have a 5 and a 9 and an 8. I could even have a 4, and a 4, right? Every single card is looked at differently. So there are 52 cards, and we need a set of 3 of them. Okay, and if you hear that word, a set of 3, set is usually a giveaway that it's a combination as well. So we need to calculate 52C3 to find out how many 3-card hands are possible. And that is 22,100. All right, how many 3-card hands contain 3 hearts? So again, if you think about the suits are hearts, diamonds, spades, and clubs, and the hearts are one of those suits. So there's 13 cards that are hearts. So how many in this 22,100, how many 3-card hands have all 3 hearts? Well, there's the ace of hearts, 2 of hearts, 3 of hearts, or there's the 7 of hearts, king of hearts, 7 of hearts. Did I already say 7? Wow, I can't remember, sorry. There's the 2 of hearts, 9 of hearts, queen of hearts. Okay, so there's all these different options. So to calculate that, we're going to do, well, there's 13 hearts. Sorry, that's not a very good 3. There's 13 hearts, and we want to know how many groups of 3 of them there would be. When we calculate 13C3, we get 286. So now the third part question is going to ask now, what is the probability that if you're dealt 3 cards, that your 3-card hand contains 3 hearts? Well, the likelihood of getting 3 hearts is the number of ways you can get 3 hearts, which is 286, out of the total number of ways that you can be dealt 3 cards, which is 22,100. So 286 out of 22,100. Now if I were to calculate that, which I'm doing on my calculator here quick, is 0.013, or in other words, 1.3%. So again, very unlikely that when you're dealt 3 cards, they'll all be hearts. Okay, so we have another set of questions right here, and these two go together. You might want to pause the video and maybe try this one out on your own. It is a little tricky. Otherwise, you can go ahead and keep watching and jot this down. How many 3-card hands contain 1 spade and 2 of any other suit? All right, notice we've got this word "and" here. We have 2 different things going on. We want to be dealt 1 spade, that's one part of the event, and then we want to be dealt 2 of some other suit. What we're going to have here is 2 different combinations that are being multiplied. Spades, remember, are one of our suits, and there are 13 of them. So out of the 13 cards, I want to be dealt 1 spade. Out of the remaining 39 cards, and that might take you a minute to kind of think through a little bit, but the remaining 39 cards, we want to choose 2 of them that are not spades. 13C1 is 13, and 39C2 is 741, and so we get 9,633. So the question here, and I'm rushing because I'm running out of time, what is the probability that your 3-card hand contains exactly 1 spade? Well, it's 9,633 possible ways that can happen out of 22,100 possible 3-card hands you can get. By the way, this calculates out to be about 0.436, so not, kind of likely, about 50-50 almost, so 43% likelihood that we would be dealt 1 spade.